So I will start with a question. And the question is, what do the following three subjects have in common? First of all, we have the study of structure on typical terms of the fragments of the linear lambda calculus. And don't be scared by the lambda calculus thing here. We will describe everything in a bit. And just to illuminate a bit the question, when I say structure, I mean the number of parameters, such as the number of identity subterms, of closed subterms, of free variables, and of unused abstractions, which we will all define later on in this talk. Second of all, we have the structure of typical trivalent maps and the relaxations. So here by structure, we mean the number of, say, loops or bridges, vertices of degree 1 and 2. And finally, the structure of typical Feynman diagrams in zero-dimensional cubic quantum field theory, with the action given by this functional here. And so, in first approximation, it seems that there is nothing common. Perhaps these two, there is something in common with them, but the lambda calculus seems completely separated. But the point of this talk is to say that there exists a dictionary relating the structural properties of objects in these three families of structures, and that we can use techniques drawn from each of the corresponding fields, so from combinatorics, from logic, and from physics, to study them in tandem. And since I'm not a physicist, I have no idea how to properly use this kind of structures, but the connection is there, and some people might be interested by this. So I just put it as a bit of a question for people if they want to study such objects. And so let us start with discussing the main actors of this work. So on one hand, we have the lambda calculus. So what is the lambda calculus? It is a universal system of computation, and it is universal in the sense that anything that, say, a theorem can do, so can the lambda calculus. So it is the strongest idea we have about computation somehow. It is perhaps the definition of computation. And so the lambda calculus is formed by a very simple grammar. We have three cases. We have the case of variables. So we have an infinite supply of variables, which we just signify by some lowercase Latin letters. You have the case of abstractions, which are of the form lambda x dot t, where t, where this represents an anonymous function. So this is a function that takes an argument x and it executes, say, what is in the body t. So t is the specification of the function. And finally, we have the notion of applications, where we have s applied to t. And this represents the act of feeding an argument t to a function s. So this encapsulates in a very minimal way functional programming or computation using functions. And so we are interested in working with these objects combinatorially, and so we will impose a kind of equivalence which is called alpha equivalence, in which we are allowed to freely name variables, taking care that we do not accidentally bind variables. So, for example, here lambda xx, the famous combinator, is alpha equivalent to lambda yy, lambda xx, sorry, lambda x applied to x. So here we just rename this x variable here to y, so there's no problem here. But this is not alpha equivalent to, say, lambda y dot y applied to a applied to lambda x applied to x. Why? Because here we have only replaced one of these y occurrences with an a. So this somehow has made this variable become unbound from the corresponding lambda, and it has changed the structure of the object. Okay, so we are interested in the lambda calculus, but we're interested. So the lambda calculus, being a universal system of computation, is quite complicated. So what we need to do, we need to put restriction on it, so we can study simpler subsystems which are easier to analyze combinatorially. So starting with the idea of general terms, where we have no restriction on variable use. So for example, here we can have free variables. This a is not bound by any abstraction occurring in this term. Here, for example, we have a variable y which never appears in the body of the abstraction. And for example, here we have a variable which is bound by lambda but appears twice. So we can have free variables, unused variables, and duplicates or triplicates, and so on of variables. So putting a bit of a restriction on this, as we said, putting a bit of a restriction in this, we can say that we can require that terms are such that bound variables occur at most once. And as such, we arrive to the notion of affine terms. And affine terms have this property that you can still have free variables, but you cannot have this kind of duplication. And of course, you can still drop variables, so you can have a bound variable here which never appears in the body. And finally, restricting even more, we have the notion of linear terms, where we require that bound variables occur exactly once. So here we have still free variables, but we no longer have unused abstraction, so we no longer have variables which are bound by never appear, and of course we cannot have duplicates. So this is the family we'll most focus on. This is the notion of linear terms, and these are somehow related to the linear logic you saw earlier in the second talk. They are somehow related by the notion of like the typed and the untyped lambda calculus, the linear lambda calculus in this case. On the other hand, we talk about maps in this talk, and maps essentially are graphs embedded in a surface, and I will not be very specific about what a surface is, but we can imagine here a kind of a sphere, for example, and we embed this k4 minus graph on it. So for us, the surface will be orientable, they will have no borders, etc., for now at least. And so for example, we have here an embedding of k4 minus, and here we have an embedding of k4. The first one being a planar graph can be embedded in the sphere, the second one is not a planar graph, and so it must be embedded in a higher genus surface. In this case, we have the torus. And so maps, in general, again, are quite complicated objects, so we would like to restrict them a bit so we can study them better. And so we say that we're interested in unrestricted genus maps, so we allow a surface with as many handles as we want, but we will put restriction on the vertex degrees. So we will mostly focus on maps which have degree 3, 1 and 2.
So you consider topological graphs?
Yes, exactly. Okay. So these are all embedding, and different embeddings give us different maps, while the underlying graph can be the same. So why would the logician, for example, be interested in maps? And we have some logicians here, so this is a legit question to ask. And the answer is given by string diagrams, which appear in the work of Bodini, Giedenberger, and Jacob, and also in the work of Noam Zellweger. And string diagrams essentially are a pictorial way of representing the grammar we already talked about, where a vertex represents a variable, a free variable. Lambda abstractions are represented by a lambda vertex with two outgoing wires, one which is on the left. Say it is the first one we see if we are doing a clockwise stir. So the first one we see, it goes into the body and represents the fact that this body T is bound is the body of this abstraction, and there is another outgoing wire which represents the bound variable. So here the order is important again, because we have to distinguish between this wire and this wire. We have to distinguish between the wire representing the bound variable and the wire representing the body. And finally, for case of applications, we have a node here labeled by the application symbol, and we have on the left the sub diagram corresponding to S, and on the right the sub diagram corresponding to T. And so we see that order matters indeed. And since order matters, we are not talking about just a graph with labeled vertices, but we're talking about a map. We're talking about an embedding, because essentially maps are graphs equipped with orientation around the half edges incident to each vertex. So here, for example, I have given you the corresponding map or string diagram of a lambda term, and you can start noticing some first glimpses of this dictionary I talked about in the beginning. So, for example, it's quite clear that free variables correspond to unary vertices. So unary vertices of the map correspond to free variables like this A here. Unused abstractions correspond to binary vertices. So here we have an unused abstraction which corresponds to this unbound, this unused abstraction. So we have here a variable V which never appears in the body. And so the corresponding lambda doesn't have a wire coming in from the right. Identity subterms correspond to loops. So we here have a little loop on the map. And this corresponds to an identity subterm lambda-w. And I call this an identity because essentially it's a function that takes an argument w and just returns it as it is. So it does nothing, it's the identity. And more generally, we can see that closed subterms are in correspondence with bridges. So here we have a bridge, and this defines a component if we cut it. And this component corresponds exactly to this closed subterm of the lambda term. And a subterm is closed if it contains no free variables. So we see here this is somehow a little subroutine which has no free variables. It has no connections to the rest of the term, and we can think of it as a bit of an isolated subroutine in our program, say. And finally, it would be nice to have a notion of size, so we can align these two objects. We talk about combinatorics, so it's always good to have a notion of size on our objects. And we can take, for example, the notion of size for maps given by the number of edges, and for lambda terms being given by the number of subterms. And this aligns nicely the two notions.
And the graphs are non-directed.
The graphs are non-directed, yeah. And so finally, this correspondence is actually a bijection between closed linear lambda terms and trivalent maps, which can be generalized to the case of affine terms. So closed affine terms are in correspondence with two trivalent maps, and this has been established in works by Bodini and co-authors. And so, on the other hand, why would the combinatorialists be interested in lambda terms? And here we have a lot of combinatorialists. So again, this is a valid question to ask. And I can give you the answer to this in the way of an example, perhaps, but an example which is kind of deep. I can give you the decomposition of open-rooted trivalent maps in the style of Tut, as was presented in a paper by Arke Béraud, starting from the edge. So we are talking about open-rooted trivalent maps, which are maps such that the root has degree 1 and every other vertex has degree 3. 3 or 1, sorry. So this is the open signifier here. And so such a map is either the base case, which is just an edge. It is, and then we can start decomposing this map by looking at the root and looking what happens around the root. So we will try first of all to delete the root and delete its immediate neighbor. And this will either disconnect the map, so it will result into two disconnected components. So here we have a term of the form z tz square, if t of zu is the generating function enumerating this kind of a family of objects. Or we can have the case that we cut the root and we cut its immediate neighbor, but the remaining map is not disconnected. And so in this case, we can canonically root on one half of the resulting, on one of the two resulting edges, and we can point at the other edge just to keep track of it. So this is given here by a differential operator. So we have kept track of all the data we need. We have canonically rooted in one edge, and we have kept track of the other by way of pointing. And indeed, this gives us a nice generating function enumerating open-rooted trivalent maps using this decomposition. But indeed, this should remind you a bit of the structure of linear lambda terms, which we said already are either of the form x, just a variable, so this corresponds to the case of the half edge or z here, or of the form st, where s is applied to t, and here indeed we have the submap corresponding to s and the submap corresponding to t, and they are joined together to give us the bigger map. Or finally, we have a case of an abstraction lambda x dot t, where x appears exactly once in t, and indeed this x that appears exactly once in t is represented by this pointed at vertex. And so we see that the lambda term and we see indeed that this generating function enumerates not only maps, but also enumerates lambda terms. And indeed, this is an occurrence of this bijection we talked earlier about. And so this, in a paper of Zellberger, is made more explicit, and it gives us a nice combinatorial way of seeing what the correspondence is. And so just to recap a bit, we have that syntactic diagrams of families of lambda terms yield maps. On the other hand, we have that that lambda terms are invariant somehow of maps which encode topological or decomposition data. And we have a dictionary which allows us to translate between the two. It allows us to translate properties of lambda terms into properties of maps and vice versa. And our plan is to use this dictionary to study both of them. And I want to stress here that it is not just using maps to study terms or just using terms to study maps, but this is a fruitful two-way connection, that we're using maps to study some properties of lambda terms and lambda terms to study some properties of maps in ways that one illuminates the other in unexpected ways that you would not arrive to just by looking at maps or just by looking at terms. And so we can talk about a little bit about previous work. So maps are, of course, a very central field to modern combinatorics. They have been studied a lot, and lambda terms are the same for the corresponding fields of logic. And so, for example, planar terms or planar maps, or generally restricted genus maps have been studied a lot. And so have the lambda terms, but with other size notions. So taking other size notions of lambda terms is also a legit move, and a lot of people have written work about the combinatorics of lambda terms under these other models. And more generally, some people have worked also on general maps, as we do here. So they put no restriction on the genus, and they're looking at parameters on these maps, but they also put no restriction on the degree of the vertices. So here we have really the general case of maps, and it's a very nice work, and somebody can like look at the distributions we have for the parameters and compare them with general maps and see that there's some very interesting coincidences and some very interesting divergences between the behavior of restricted and unrestricted maps. And just to compare a bit, our work will focus on the following families. First of all, we have rooted closed trivalent maps, which are in bijection with closed linear terms. And here the closed signifier says that you have trivalent we have maps which are regular of degree 3, except for the root which has degree 1. More generally, we have open trivalent maps which are in bijection with open linear terms. And here the open signifier means that we have maps which have allowed degrees in 3 and 1. And finally, we have maps with allowed degrees in 2 and 3, which are in not exactly in bijection. There's a little bit of a perturbation, but they are in correspondence with closed affine terms. And our results are in the form of limit distributions. So limit distributions of parameters, and in this case, for example, for the case of closed trivalent maps and closed linear terms, we can start by looking at the distribution of loops. And the distribution of loops corresponds by this dictionary we mentioned before to the distribution of identity subterms in the corresponding lambda terms. And so here we're looking at loops in our maps, and we want to see what is the number of these loops. And so here I have a lambda term, lambda x, lambda y, y applied to lambda w, w, and all of these applied to x. And this is represented by this map here. And I have highlighted the unique identity subterm here and the unique loop on the corresponding map. And in this case, it is a bit surprising, but at least to me it was surprising. But the corresponding limit distribution is the Poisson distribution with parameter 1. So we have that if x is the random variable counting the number of loops in a random closed trivalent map, as n goes to infinity, this converges in distribution to this Poisson distribution we have here. So we can see here a bit of an experiment of sampling, actually this is by brute force, counting all possible terms and plotting the corresponding distribution, and it's quite clear that it converges exactly to this nice Poisson limit distribution. So the next result is somehow a generalization of this. So the loops somehow are the easiest, or perhaps the smallest, it is the smallest case of it is the easiest case, or the clearest, or the most trivial case somehow of a bridge occurring in our map. We have a bridge here, and on one hand we have like, if we delete this bridge, we have a quite complicated component, but on the other hand we have quite a trivial component. This is just a loop. So if we instead look at bridges, but we allow more complicated objects to appear on the other side of the bridge, we have of course something like that. We have like a more complicated map appearing on the other side of the bridge, and here we're starting to look at the distribution of the number of bridges, which corresponds to the number of closed subterms, as we already said. And here again we have a lambda term. We have highlighted the closed subterm, and this is the corresponding component which would result after the removal of the bridge. And so here once again, even more surprising perhaps, we have exactly the same limit distribution. We have that the number of bridges converges in distribution to the Poisson distribution of parameter 1. And this is quite surprising actually, because it says that if you take a big trivalent map and you try to look at the number of bridges, you will see perhaps 1, 2 of them, but not more. So it is not like in random graphs that after a point there is a phase transition and everything becomes connected, because bridges still remain. You can have 1 or 2 bridges, and you will often have 1 or 2 bridges. But on the other hand, it does not happen that you have a lot of bridges. So this is quite of an interesting situation. And in fact, this result doesn't, like half of this result perhaps, doesn't only hold asymptotically, but it is also a combinatorial fact that using techniques from lambda-calculus, you can prove that maps which have exactly one bridge are in correspondence with maps which have no bridges. And this is quite a nice bijection, which is quite natural from the viewpoint of lambda calculus, but it is not as obvious from the point of maps. It is not an operation which is natural, perhaps, from a map theoretic perspective. Finally, passing to the realm of open trivalent maps, which are in correspondence with open linear terms, we have the distribution of unary vertices. So here we have a map with allowed degrees in 3 and 1, and we are looking at unary vertices, which I have highlighted here. And this is in correspondence with free variables in open linear terms, and the corresponding law this time is a continuous law. So in the previous two cases, we had a discrete law, we had a Poisson law. This time we have a Gaussian limit law. So after appropriate rescaling, we have a distribution in converges in distribution to the standard Gaussian for parameters mu and sigma square given here. And so quite a similar situation is present when we look at the 2-3 valent maps. So here we allow degrees 2 and 3, and so for example here we have binary vertex, which are in correspondence with closed affine terms. And here we are looking at the variables of the degree 2 nodes, which I have highlighted here in red, which corresponds to the number of unused lambdas in affine terms. And once again we have a Gaussian limit law, but this time the parameter is different. So quite a strange value. We have n to the 2/3. And once again, after appropriate rescaling, we have the Gaussian law we want. And so our workflow for deriving these results is quite streamlined. First of all, we start with by establishing good bijections to obtain specifications for the bivariate ordinary generating functions. And here I say good because we have a lot of this kind of bijections and decompositions, but not all of them are tractable, and not all of them give us a handle on all kinds of parameters. So each parameter, it somehow like forces us to use a specific kind of a decomposition, a specific kind of a bijection. So we have here the first step, which is establishing the good bijections we want. Then this leads invariably to generating functions which are purely formal. So here we have generating functions which do not correspond to, say, they don't represent some analytic function. So we have generating functions which have a radius of convergence 0. And this makes them difficult to analyze because in analytic combinatorics, at least, we are used to having nice convergent power series, and we can then use techniques from complex analysis, contour integrals, quasi-power theorem for deriving limit distributions, etc. So we no longer have access to this nice tools from complex analysis. And this necessitates the second part of this workflow, which is developing new tools to analyze purely formal generating functions. And we do this in two ways. First of all, we make a schema based on ordinary differential equations, which yield Poisson limit laws, which we'll use to derive the first two limit laws. And the moral of the story, perhaps, is that pumping the equation, so looking at higher and higher derivatives of the generating function of interest, we can see that only certain terms contribute. And this will perhaps we'll give a bit of an example later on. And the second tool we develop is a schema based on compositions, of which there exists a lot. There's a nice ecology of composition-based schemas in analytic combinatorics, which discuss various interesting properties of compositions where F and composed with G interact in different ways based on whether F is analytic, G is analytic, both are analytic, etc. And so perhaps the archetypal work in this area is the work by Bender, on which our work is essentially resting on, and it's a bit of a straightforward generalization. We have compositions of the form F ZU G of ZU, where both F and G here count some combinatorial object, perhaps, or F is the logarithm, as we'll see later on. And we see that for compositions of this form, which occur quite often in combinatorics, we have an inheritance of the limit laws of G itself under appropriate conditions for G and F. In fact, roughly speaking, we want F to be nicely behaved, so we want F to be analytic in both variables at the origin, and we want G to be badly behaving in the sense of being purely formal, of having a high enough rate of growth in its coefficients. So if these conditions hold, then we have indeed an inheritance of the limit laws of G for the structures given by F composed with G. So I can give you a bit of a proof sketch for the first result, which is the number of loops and identity subterms. Sorry. So we start with a decomposition, as we said. The first step is always to start with a nice decomposition, and this kind of mirrors a bit the decomposition I gave you in the beginning, the two-style decomposition, the topological cutting the root thing. So we can start with either the base case, which is and here I'm missing a little bit. I'm missing a unary vertex connecting to this vertex here. But anyways, we're starting with a loop, which is the smallest possible closed trivalent map. And then I have the case where, as before, I can cut the root and its immediate neighbor and separate the map into two. So this is exactly the same as before. Or I can have the case where I can cut the root vertex and the immediate neighbor, and this gives me a connected map. And so in this case, we can notice a nice correspondence between such structures and structures with a highlighted loop. And the idea, roughly, the moral of the story is that we can take this vertex here and slide it all the way down to create a loop. So this is very informal, but this is pictorially what's happening. We can take this vertex here and we can slide it all the way to form a loop. So there is a correspondence, the bijection between these two structures. And indeed, this will give us a nice genetic function, functional equation for our genetic function here, where Z counts a number of edges and U counts a number of loops. And so we can start pumping this equation. So we can start taking derivatives. And the idea here is that every time you take a derivative, this will lead you, if you analyze asymptotically the coefficients of the derivative, this will lead you to essentially finding the asymptotic moments of the distribution you are interested in. So we can start with the mean, for example, taking the first derivative with respect to U. We have this equation here. And we can see that asymptotically this grows as the original equation. It grows as the coefficients of this equation. And here I'm using this coefficient extraction operator, which says that I'm looking at the coefficient of Z to the n in this power series. And so the first step, we see that it leads to exactly the same asymptotics as the original genetic function evaluated at U equals 1. So we see here that the mean, it grows the same as the mean will be 1 essentially, because the coefficients of the derivative evaluated at U equals 1 grow the same as the original function. The coefficients of the original function. And we can do this again. We can take the second derivative. We're looking at the second factorial moment. And we see once again that here, by replacing the derivative, so by U, with the formula we found before, and this is the pumping step, we see indeed that we have a new equation, quite a few terms at this time, but again, all of these terms will not contribute, and the only guy that contributes is essentially the original genetic function. So once again, for the second factorial moment, we have this interesting behavior. We have the second factorial moment being 1, and we're gonna keep going essentially by applying the results of the previous step each time to the next one, and we obtain essentially that for each step this kind of behavior occurs, that the only guy that contributes essentially amounts to the same coefficient asymptotics as the original genetic function. And so indeed, this by our schema, it's quite clear what happens. It's that every factorial moment becomes 1. By our schema, this yields Poisson 1 limit laws. And here you have to use a bit of a convergence theorem for the corresponding moment generating function, etc. But it's quite straightforward that this gives a Poisson 1 limit law. So we can try to do the same thing for bridges and closed subterms. And this time, it's not going to be as easy. But the essence is the same once again. We can start by defining an interesting class of objects, first of all, which we'll use to derive the bijection we want, because as we said, the first step is always to have a nice bijection. So we can see that these lambda terms, they essentially define a spanning tree, a very unique spanning tree with very interesting properties in a map. So for each map, here we have the map, we can single out the spanning tree defined by this the corresponding lambda term. Now, suppose that we have a map where we have a highlighted vertex of degree 2, which we can think of as somehow a vertex which we have deleted one of its incident half edges. So, given a map with a highlighted vertex of degree 2 and the spanning tree defined by a term, we will define the class Q of maps such that the unique path from the root to this highlighted vertex contains no bridges. So this might look a bit artificial at the first view, but we can use this class Q as a building block for analyzing maps with a highlighted bridge. So suppose I take a map here with a highlighted bridge. So we see we have a bunch of bridges, but I have highlighted just one of them. Now, somehow we need to cut down this map, like decompose it into members of Q, and this happens as following. We once again consider the unique path from the root to the endpoint of the highlighted bridge closest to the root. So this is our path here, and we can start noticing that we can start cutting off every time that this path somehow enters a submap and exits it again. We can like consider this as a separate Q object. So indeed, what happens is that here, for example, the first component will be this one, which is kind of a trivial component, and so is the second one. We have the path entering and exiting from the same vertex, and indeed this has as a map, it has the property that the unique path from the root to the root of itself to the highlighted vertex, if we consider this one to be a highlighted vertex, has no bridges. So trivially, this holds for the first and the second maps. But here we have a more complicated case. We have that the path enters from here, from what would be the root here, travels on, and then exits again later on. And see, indeed, here we can consider this to be a highlighted vertex of degree 2 like this, if we cut the bridge here. And we see that indeed it has the property that the path from the root to the highlighted vertex contains no bridges. So indeed, this Q class forms the building blocks which we can stack on a path to create any map with highlighted bridges. And so this, after a bit of a manipulation, it gives us a quite scary functional equation for our generating function, which once again may be pumped using our schema, but here the pumping is quite a bit more complicated and I don't want to go into it. But morally, the same kind of deal happens, is that every time you pump, you see that only one term or a sum of terms contribute anyways, and somehow magically this ends up being asymptotically the coefficients contribute exactly the same as the original generating function. And so now for the case of vertices of a given degree in open trivalent maps for the beginning, we can start with a completely different kind of specification. And here we see that indeed we can have a lot of specifications, but some of them force, like some parameters force a specific viewpoint on the object at hand. And so here we completely change our viewpoint. We go from a nice decomposition-based viewpoint to this specification based on the exponential Hadamard product. So the exponential Hadamard product is quite easy to explain. It's that you take two power series and you coefficient-wise make a product multiplied by appropriate factorial or inverse factorial weights. But in any case, this is what happens. It's a coefficient-wise multiplication. It's not the Cauchy product. And so here we have this kind of specification, which is quite well known. It was, for example, in the paper by Bodini and co-authors. And the moral of the story, the combinatorics that it encodes, is the following. We can start with here essentially we have the exponential of z to the 3 divided by 3 plus u times z, which counts permutations such that we have allowed cycles of degree 3 or 1, and we are tagging the cycles of degree 1. This essentially gives us some kind of a configuration model for graphs. And the configuration model works as following. We start with a bunch of vertices, each one corresponding to one of the cycles of this permutation. And we glue to them 3 or 1 half edges according to the permutation at hand. So we have a permutation with allowed cycle length of 3 and 1, and this represents this bunch of vertices with 3 or 1 half edges incident to them. And now we have almost a map, but we need to glue these half edges together to form the proper map. So this data is given by another permutation. So here we have a permutation where all cycles are exactly of degree 2. So we have here the exponential of z squared over 2, which enumerates this kind of permutations. And indeed, I have here the blue is not quite visible in the screen, but this permutation, it gives us exactly the data of how to connect half edges together. So example, we can we can glue this half edge to this one to this one, etc. So one of them gives us the information of what half edges are incident to each vertex. The other permutation gives us the information of what half edges are glued to what other half edges. And essentially, this way of giving maps gives us exactly, not necessarily connected, open trivalent maps. Sorry. So since we are interested in connected maps, we are taking the logarithm, which is, for combinatorial reasons, the way to take a connected component of a not necessarily connected object. And finally, we have some routing operation. So here we take a derivative by z to root. We're always interested in routing maps. And we have some initial conditions. And the same kind of deal happens with two trivalent maps. But this time we need to change a bit this second permutation. Instead of allowing degree 3 and 1 as before, we allow degree 3 and 2. And once again, we're using a variable to mark the degree 2 cycles in this permutation. And so indeed, here we can see that the Hadamard product is essential because it says that as many atoms exist in this first permutation must exist also in the second permutation. So this exactly allows us to align the appropriate notions and allows us to make a proper not necessarily connected map. And of course, because of some technical reasons, the true generative function of affine terms is not exactly the one of maps, but it's a slight perturbation of it, a little bit. You have to act on it with this z squared over 1 minus z term. But in any case, the idea is that you have essentially a map plus something which is quite easy to describe. It's just a path. And this is just the technicality. We will not care about it too much. Okay.
Alex?
Yes?
Sorry, perhaps I missed on the previous text.
Sure.
But when you say exponential Hadamard product, so you have your number of guys divided by n factorial.
Yep.
This is your coefficient.
Yep.
And when you do the Hadamard product, you have one factorial.
You have to cancel one of the factorials, I think. Like in the end, you should be left with. Maybe I'm saying something stupid. I don't remember the definition. I think you have to be left with an n factorial on the denominator. I think so, because these are we can check the specification later. I forget about it all the time. But essentially, these are exponential generative functions. I don't want to mention this, but it's a bit of a fun fact is that you can start here. We start with exponential generative functions. And somehow in the end we end up with ordinary generative functions. And what happens is that this is a phenomenon called rigidity. It happens that maps have non-trivial automorphisms. So no non-trivial automorphisms. So we start with an exponential generative function. So when we combine them, we still want to have a exponential generative function. So we want to cancel one of the factorials. So we are left with just an n factorial on the denominator, I think. And then somehow like magic happens, and this fact that we take a connected submap and we point at it drops us to the world of ordinary generative functions. So this phenomenon of rigidity is very clear here. Does this answer your question? Yeah. Okay. So here the tool is no longer the Poisson-based tool we had before. So no longer we have a differential equation. We kind of do, but we don't care about it too much. Here this time we have a composition. We have something composed with the logarithm, composed with differential operator, etc. And so here, the basic tool will be this kind of like generalized Bender theorem where we have f of zu composed with gzu. And we want f to be nice, so we want f evaluated at u equals 1 to be analytic at 0. And we want that g has the property that the n-1th coefficient is dominated by the nth coefficient when evaluated at u equals 1. So we have g being badly behaved, f being nicely behaved. And so if this holds, this theorem allows us to encapsulate the following folkloric notion that follows perhaps directly from Bender's theorem. If we say that f is the generative function of some class, combinatorial class f calligraphic, and g is the one of g calligraphic, then morally what happens is that we say that to build a big f composed with g structure, we have to pick a small f structure and replace one of its atoms with a big g structure. This is the most efficient way to do it. You pick a small f structure and you compose it with a big g structure, because there's a lot of g structures. We see here that the number grows at least factorially. No, it could be less than factorial, I think. Anyways, it grows fast enough. So G has a lot of options. F doesn't have as many options, so the best thing to do is just pick a tiny f and a huge G. And of course, if you have a huge G component here, anything that happens that is interesting invariably will fall inside G. So this theorem allows us to say that indeed this folkloric notion is correct. If f, on the other hand, is the logarithm like we have here, this allows us to encapsulate a different folklore idea in combinatorics. It is that asymptotically, almost all not necessarily connected G structures for appropriate families G are connected. And this happens, for example, in random graphs. You can see that asymptotically, almost all random graphs are indeed connected. Almost all not necessarily connected random graphs are indeed connected. And this can immediately be proven by applying Bender's theorem. And so essentially, what happens is that the distribution of parameters is the same between a connected and a not necessarily so structured, because asymptotically, almost certainly, all structures in G are connected. And so using this tool, we can now begin to analyze this specification we have. We can, first of all, we have here nice exponentials. So these are all, can be analyzed uniformly in U around U equals 1 using saddle point analysis. A more general case of it, which appears in the works, for example, of Darmota and Giedenberger and their co-authors. So using their frameworks, we can have a nice saddle point analysis of the coefficients of each exponential. And then the exponential Hadamard product is very easy to analyze. You just take the coefficient asymptotics, you multiply them, perhaps you need to cancel some factorials, but anyways, everything here is nice and classical. And both of these yield Gaussian limit laws by very standard tools like, I don't know, quasi-power theorem, and stuff like that. So we have done all the work we wanted for not necessarily connected maps, and now somehow we need to pass to the realm of connected maps. But as we said before, our schema says that essentially this is the same thing, like not necessarily connected maps and connected maps asymptotically the same thing. And so this allows us to pass to the realm of connected maps, and then the routing does nothing because the routing just selects a vertex, so it does not change our distribution. And so everything happens nicely. Here we just have some shifts by size, but nothing interesting happens. And the same is true for the sled perturbation I talked to you about. Here we multiply by z squared over 1 minus uz, but this is analytic. So once again, we can apply our schema. And so finally, we have that the Gaussian limit laws we found for the innermost expression transferred to the whole genetic function. And so we have the results we wanted. We have the Gaussian limit laws. And so I see that I have perhaps 3 minutes left, 2 minutes. I will talk to you very quickly about the number of beta radices. So far we talked about lambda-terms, we talked about maps, but we stayed on something very static. We described structural properties, and a lot of people are interested in dynamics. Rewriting, for example, the talk of Nicolas Baer in the first day. And so perhaps I will give you a little bit of an example of a rewriting system on maps and lambda-terms, which is that of beta reduction. Beta reduction essentially encodes computation. So we talked about lambda-terms as a computational tool, but we never saw how computation happens. And essentially the idea is that you have a lambda-term and you have an application of a lambda, of an abstraction to something else. You can feed the something else into the abstraction and make one step of your computation. So to understand the mean number of steps before you reach a normal form before your computation ends, you can start by counting beta radices. And essentially, the idea here will be given by a very standard decomposition for closed terms. We can start with an identity as always. We can have applications as always. And finally, we can have abstractions. And the abstraction can come in the form of taking a map, selecting an edge, and then cutting on the left and connecting to the top, or cutting on the right and connecting to the top, or cutting on the left and connecting to the top. And by some combinatorial tricks, we can start tracking the radices. So every time we have an application of a lambda to something, this counts as a redex. Every time we have an application of something which is not a lambda, it doesn't count as a redex. And we can do the same thing perhaps for abstractions. The case here it's really proof by picture. And if somebody wants to discuss it, we can surely do after. But anyways, we can analyze this. It's a bit of a mess, but anyways, in the end, using some facts about lambda-terms, we can arrive to this differential equation, and we can start pumping. It's our favorite tool now. And we can plot a bit the distribution, and we see that indeed the mean number of beta radices asymptotically evolves as k over 8, and the variance evolves as this expression here, 39k over 320. So this gives you quite an interesting lower bound for the distance to normal form. So it says that if you have a term with three k plus 2 subterms, then it takes k over 8 steps to reach, on average, a normal form. So what's next? We would like, of course, to study more parameters, so mean path length, for example, profile of a map, etc. And of course, we would like to extend these connections between maps and terms to more families like planar maps, bridges maps. This has already been done in works by Noam Zellberger. And we would like to look at the distribution of parameters in these two. That's it. Thank you very much for your patience.
Thank you. Questions?
Yes. So you showed that you had a lot of analysis of different parameters on maps, lambda-terms, and so on. And the limit laws that you were showing were Gaussian, Poisson, and so on.
Yeah.
Do you have examples of more exotic limit laws? For example, the last image, you know what is the limit law in the last image?
This one.
This
one.
Yes, this
Great question. In the beginning, we thought it was Gaussian. It doesn't look so Gaussian after all. I don't know. The problem is that this is quite complicated. And so I can only give you the mean and the variance, and I can maybe give you higher moments, but I don't see any patterns. And I cannot really guess. Like I can try pumping more, and then I can tell you a bit of a more informed opinion. But k over 8 and like the mean and the variance kind of play nice with the Gaussian. Like they cancel nicely, and you have like normally you have the quadratic variance here, but something cancelled, and you have linear mean, linear variance. So this looks a bit Gaussianish. So perhaps it is Gaussian.
So this one is still open. And
yeah.
One proven case of a parameter which is leading to some, let's say, exotic
one. Not this one, but the work by Olivier and Sergei Dovgal and Olivier Bodini and Singh Huang, Julien Courtiel, they have for general terms, for general maps, they have some kind of like completely new distribution given by a triangular array of coefficients and stuff. So it can happen that in general maps you can have quite exotic laws. Here everything looks standardish, Poisson, Gaussian, stuff like that. I don't know. Perhaps for the distance to normal form, maybe it will be Gaussian after all. I have not looked at it too much. It looks kind of sharply picked. Anyways, nothing like proven, nothing. Yes.
So maybe it's more a comment. So you have the number of vertices, but then when you rewrite, they may create new vertices.
Yes, perfect.
So I mean, even experimentally, have you tried to see the length of that you need to get to the normal form? Yes.
So Noam has done a lot of experiments, and this n over 8, the k over 8 becomes k over 7. So on average, it seems experimentally that the distance to normal form is k over 7. So what happens is indeed that we can this is a lower bound indeed, k over 8 is a lower bound. You start with a beta radius, but every time you reduce, it can happen that it creates new beta radices. Essentially, this can happen in 3 ways. There's 3 well-known patterns that generate new or keep the same number of beta radices. And so I have analyzed 2 of them. And the third one, which I thought was the easiest one, is the one that I'm still struggling to do. So for the other 2, I can give you also the mean. So I can tell you on an average lambda-term how many radices there are and how many occurrences of each of these patterns are. And there's a bit of an overlap on them. But anyways, like you can try like slowly. We are getting to a tight bound on the mean. So indeed, the k over 8 will after analyzing everything nicely, hopefully will become k over 7.
Yeah, but k over 7 is for the rewrite, the whole rewrite.
For the whole rewrite.
Not the number of vertices.
Yes. For every step?
No, what I mean is because you have creation.
Yes.
And so...
we can, you mean track the overall number of... this would be interesting.
And so,
also.
You see, because there is a connection with what Nicolas Vert was speaking about yesterday.
But so you can derive this from...
Cascade,
yes.
A rewrite creates a new rewrite.
Yeah.
So this is what Nicolas called tracelets.
Yeah.
I was wondering
I think you can derive this by knowing how many beta radices you started with and comparing with the size of the the path until you reach the normal form. So the difference would be the extra beta vertices what were created along the way, right? So
yeah. But that's what you're looking. That's what you're looking at when you told me you look at the three different ways.
Yes, the patterns. Yeah.